These are the notes for AP Calculus on the topic of limits at infinity and horizontal asymptotes. So remember, we've got limits at infinity there's two types. The limit as x approaches positive infinity, which, if you look at the far right of the graph, could be heading up to infinity. It could head down to negative infinity, or it could have some horizontal asymptote, like with some constant. And the graph gets closer and closer to that. Or it could be non-existent if there's nothing that goes to the right forever. And then the other possibility is we have limits as x approaches negative infinity. And those, if you look at the far left of the graph, again, it could head up to infinity, could head down to negative infinity, or again, you could have some horizontal asymptote. It could be the same as the one on the right or different. Depends on the function. Or it might not even exist if there's nothing over there. So graphically, that's what that means, remember. So oftentimes we're asked to figure out what these are without the graph. So let's take a look at first some things we didn't quite look at before in AP Calculus AB, and that's comparing some different types of functions and their growth rate. So as x approaches infinity, all of these become infinite, but they do so at different growth rates. We've got exponential functions, where b is something, the base is something greater than 1, like 5 to the x. We've got factorials, where it's x factorial. We've got logarithms, where the base is greater than 1. And we've got power functions, x to the n. And then we've got, this one doesn't really have a name here, it's just x to the x power. The base is infinite, and that's it. So, well, I put a little number line here, which one grows smaller and which one grows larger, because sometimes it's to figure out these limits. So the one that grows the slowest is the logarithmic one. Okay? So if you have the log base b of infinity, that is infinity, but it grows pretty slow. If you remember the graph of a logarithm, you can see why that would be. The basic logarithm goes through 1, 0, and has an asymptote there of the y-axis. So it does go off to infinity, but not very quickly. And the next one is our basic power function, where we've got some exponent that's positive. This could be a square root graph. It could be a x squared graph, linear. So infinity to the n power. That's the next largest. Okay. Then larger than that, we saw this before, exponential ones, like 2 to the x or 3 to the x, where the base is greater than 1. Those grow even faster. So that'd be like some base greater than 1 to infinite power. Infinity, and the exponent matters more than infinity to the base. And then one that's even larger than that actually is the factorial. So infinity factorial. To see why that is, you can think, well, that's that would be like, remember, like if it was 5 infinity, 5 times 4 times 3 times 2 times 1. So infinity factorial, you can think of that as infinity times infinity minus 1 times infinity minus 2, and so on. So these are all almost infinite, essentially, if they multiply together. As opposed to b to the infinity would be like 3 to the infinity and an infinite number of 3's multiplied together. Here we almost have an infinite number of infinities multiplied together. And then the largest one, which might be a little more obvious, is this is if you have infinity to the infinity power. Because there you do, it is bigger than infinity factorial, goes faster than that, because this one they actually, instead of infinity, infinity minus 1, infinity minus 2, they're all just infinity times infinity and times infinity, so it's a little bit larger than infinity factorial. So it grows even faster. So again, all these are infinite, just they grow at different, get there faster. Some get there faster than others. I guess you know they all grow at whereas this one grows the fastest. So that's how we're going to utilize this kind of rank of which one grows faster, which one grows slower to infinity, to determine some different ones. So let's see how that works in the problem here. So again, the first thing you do, you substitute in infinity or negative infinity, analyze it. So on this one, we have infinity factorial over e to the infinity. So remember, we saw the factorial one is larger than the exponential one. So if the numerator is larger, then it just becomes infinity. And it says find the limit and write the equation of any horizontal asymptotes. If it's infinite, infinity or negative infinity, you don't have a horizontal asymptote. Next one, we've got subject infinity to the 999th power over pi to the infinity. Okay. Well, this one, even though the power is really big, an exponential one, pi to the infinity, with infinity of next pi, actually is eventually larger, much larger than infinity to the 999th power. So this is larger. So when the denominator is larger, we get 0. And that means we have a horizontal asymptote. Whenever you get a constant that's non-infinite on these limits of infinity, there's our horizontal asymptote. Then the next one, if we substitute infinity in, we get the natural log of infinity over square root of infinity is the same as infinity to the 1/2. So remember, power power ones, functions like this, infinity to some power, in this case to the 1/2, grow faster than logarithm ones. So this one's larger. So again, we get 0. And again, we have 4 equals 0. And then here we've got infinity to the infinity power versus infinity to the factorial. We saw that infinity to the infinity power, that's larger than infinity factorial. So when the numerator is larger, again, we get infinity. Let's take a look at some other ones here. So here we look at, when we have polynomials, you can just look at the highest exponent. Notice this one, x is approaching negative infinity. So you have negative infinity to the 5th. Divided by, on the denominator, but one with the highest exponent is the squared, so it would be negative 3, negative infinity squared. So here you can simplify. Now let's reduce the exponent here, but subtract the exponent, so you have negative infinity cubed. Well, that works out to be negative infinity over negative 3. And negatives cancel out, and we have infinity on the numerator, so this is infinity, and no horizontal. So that exponent of 3 actually mattered, because if it had been an even exponent, then this would have been a positive infinity over negative 3 would have actually ended up being negative infinity. Positive. Let's try another one with negative infinity. Those tend to be a little trickier there. So here we've got the square root of negative infinity squared over 3 times negative. So you got to be careful what you simplify first. You might think the square root and the square just cancel out, giving you negative infinity. Remember, the principal root like this can never give you a negative number. So really, you would first square it, making it positive infinity squared, and then it becomes negative 3 times infinity. And then take the square root, just gives you infinity over negative 3 infinity. Here, when there's an equal amount of infinities on the denominator, they grow at the same rate, so those reduce out. And we're with a constant of negative 1/3. And since we have a constant, we have a horizontal asymptote of y in the negative direction. All right, take a look at a few more here. So for this next one again, look for the largest exponent. So on the numerator, that's the x squared, so it would be 4 infinity squared. This time it's just infinity we're substituting. And the denominator, the cube, so negative 5 infinities cubed. 2 of those reduce out, leaving you with 4 over negative 5 infinity. And again, whenever you end up with infinities on the denominator, the answer is 0. And it's constant, so you have a horizontal of equals 0 right on the x. And for the next one, if you substitute in negative infinity, the polynomial, the terms with the highest exponent, so negative infinity to the fourth over negative 2, negative infinity to the fourth. Let's reduce out completely, and you're just left with negative 3/2. That's our limit, and that means, again, we have a constant, so our horizontal asymptote would be y equals negative 3/2. Let's take a look at one with a trig function now. So here you'd have sine of 3 times infinity on the numerator over infinity squared is going to matter on the denominator. So here, to see what this is going to approach, you just know the basic graph of sine. Between 1 and negative 1, and fluctuates back and forth here. But then that's divided by infinity squared. That gets huge. So we get this really tiny number between 1 and negative 1 divided by a huge number. That's going to approach. The denominator is much larger. And again, we have a horizontal asymptote. The difference is this horizontal asymptote, because the numerator goes back and forth between positive and negative, it ends up looking something like that, where it keeps getting crossed over and over again, but it's still considered a horizontal because it gets closer and closer. Then the next one, sometimes you might have something in factored form. You could multiply it all out if you want, or really you just have to look at the term with the highest exponent. So the numerator gives us the highest exponent, x cubed. And the denominator, we've got 3 terms. So first, you can multiply 3x times negative x, would be negative 3x squared. And then multiply that by 1 more x, would give you negative 3x. And then when you substitute infinity, those are the only terms that are going to matter, the terms with the highest exponent. You can see the infinity is completely reduced out again. And we're just up with this 1/3 is our limit. And that means we have a horizontal asymptote of y equals. All right, look at a few more here. Let's look at one with some radicals here. So this one, as x approaches negative infinity. Again, with radicals with negative infinity, you have to be careful. Notice we've got an odd root here of 3, odd root of 5, odd root of 3. Those are all fine. However, right here we've got a square root, and you can't have a negative inside the square root. It's going to be imaginary. If you have any even roots and you're substituting negative infinity, that's going to be designated. This is the case where the graph doesn't even head towards negative infinity. This one with negative infinity, notice they're all going to, this is a cube root, 5th root, 7th root, cube root. They're all odd roots, so this is okay. So what you do is you still want to use the highest exponent. So you've got 2 to the 1/3 versus x to the 3/5. 3/5 is larger, so we'd have infinity to the 3/5. The numerator is going to matter. And then we've got the x to the 1/3 and x to the 1/7. Or 1/7 is going to matter. Sorry, 1/3 is larger than 1/7. But to see how that simplifies, oops, these are both negative infinities. Sorry about that. To see how it simplifies, you want to get a common denominator. So we'll have 15 in this case. So this would be negative infinity. If you multiply by 3 and 3, that's going to be 9/15 over 3. Negative infinity multiplied by 5 and 5 is 5/15. And we simplify by subtracting the exponents again. So that's going to be negative infinity. 9/15 minus 5/15 is 4/15 over 3. And here's where the in radical form matters here. what this fraction actually is. So it would be the 15th root of negative infinity. So an odd root of a negative number keeps it negative, but it's raised to the fourth, an even power. So that's why it becomes positive infinity over 3. Right. So all these were just given as limits, but sometimes you might have to realize that that's what you're supposed to do. Remember, on all these that we had specific numbers here, like -1/3, -3/2, 0, 0, we had horizontal asymptotes. So if you're ever asked about the horizontal asymptotes, let f be this function, what are all the horizontal asymptotes of a graph of f? You have to realize the way to find those is to find the limits at infinity and negative. Limit of x approaches infinity would be 3. Sorry about that. Infinity, 3 minus 2 times infinity, 5 plus 2 times infinity. So here you can see the 2 to infinity are much larger than the 3 and 5. So those are negative. So you just end up with negative 2 infinity over 2 infinity. And then those have the same base, same exponent. If completely reduce that, just gives you negative 1. Okay. So we got a specific number. So S is for the horizontal asymptotes. So one of those is y. And that might be the only one. It could be the same on the other side. On the other side, negative, they might not have any. But there could be a difference. So you always want to check both of them when you're trying to find a couple. So when this x approaches negative infinity. Got to be a little more careful oftentimes with negative infinity. So we have 3 minus 2 to the negative infinity over 5 plus 2 to the negative infinity. And with a negative infinity, can't just move it here because we've got the 3 and the 5 other terms here. So you can rewrite it though. This is the same as 3 minus 1 over 2 to the infinity. That's what that negative x1 does. And this is 5 plus 1 over 2 to the infinity. So 1 divided by 2 to the infinity, since those are so huge here, both of those are 0. And notice the 3 and the 5 are actually much larger than those. So that's what matters. So on the other side is x approaches negative infinity, a different horizontal asymptote of y. So this actually. All right, let's go one more here that involves logarithms. So a and b are positive constants, then what is this limit equal? And they're telling you positive constants, so you know that you don't have negative values in here in these logarithms, so they actually exist. So you'd substitute in infinity into those. So you'd have natural log infinity, sorry, for x, not for so a times infinity plus 5 over the natural log of b times infinity squared. All right, so this one's they're both natural logs here. The plus 5 and plus 1, you can see they're added to the infinite, so those are negligible. So those are negligible. We've got natural log of a times infinity over the natural log of b times infinity cubed. Okay. Then what to do next here to simplify this, to see what it simplifies to be, is to remember some of your log properties. So we've got, remember the natural log of x times y. One of those log properties, since logs are exponents, you can just add them. It would be the same as natural log of x plus. So that's the log property we're going to use next. Is natural log of a plus natural log of infinity. And this one will be the natural log of b, natural log of infinity cubed. Then, remember, a and b are positive constants. So natural log of a constant is going to be much smaller than the natural log of infinity or infinity cubed. So these become negligible now. And then you can use another property of logarithms to help you out. Remember the one that says you have the natural log of to the y, bring that exponent out in front and say that's the same as y times the natural. This times y times the natural log of x. So that's what we can do here. Our next step, we have the natural log of infinity. Could bring that 3 out in front of this one, so it becomes the same as 3 times the natural log of infinity. And then we can finally see we've got the natural log of infinity reduced out with 1 to so, which means this one doesn't have one opposite. And that concludes notes for AP Calculus on the topics of limits at infinity and horizontal asymptotes.